Okay. Oh. I can tell y'all are just as drained as I am. So this ought to be productive. No, it was pretty weird. This is how sad it gets. Like at 1 o'clock, I had a Zoom meeting with a representative from a publisher, and so it connects, and I can see myself on the camera that she's seeing, and I look really blurry. It's like, am I coming in blurry? And she said yes. It's like, oh, so, maybe the webcam lens might have gotten smudged or something. So I took care of it, and I thought, well, wait a minute. Well, I had class this morning, and so I was probably blurry then too, and no one said anything. And that's the sort of thing that happens all the time. But there's something like that going on that, if brought to the instructor's attention, can be easily fixed. And yet, it's like, so, yeah. Things we'll put that in the things I should be used to by now column. Okay, but something for y'all to be used to also, if not already. That's what I should do. I should show the classes like something written on my forehead or something, and see if anybody says anything.
I think it's one of those things where like you wait for somebody else to say something about because you're not brave enough, but then like everybody else is doing the same thing, and so just nobody says anything.
Yeah, pretty much. So, yep. Well, no, sometimes there could be a phenomenon like that in faculty meetings also. Yeah, this is we're very much a let sleeping dogs lie if at all possible kind of situation. So, but since both of you will be continue taking classes with me into next semester and possibly beyond, if there's a place to start being brave, this is it. So consider it your training ground. Okay. All right, let's get the old screen share going. But yeah, it's easy to think that if you're thinking something, whether it's something like that or it could be something else like, oh, I'm not understanding this, it's the natural conclusion is that because you are not saying, no one else is saying anything, that you are the only one who is feeling that way. And it's usually the opposite, that whatever's going on, everyone is reacting to it in much the same way. Okay. Now, my computer is not being very cooperative. Okay. I'm gonna try shutting down my browser and see if that helps. It seems to be chewing up a lot of memory. I'm trying to get to typing, and it just doesn't seem to want to let me do that. Come on. Ugh. It's been kind of like this all day. Maybe the message I'm supposed to get is that, yes, I really do want a new computer for Christmas. Okay, now everything is freezing up. This is even better. Come on. Okay. All right, the browser finally shut down, so hopefully I can get things going now. Okay. So what we've seen so far is interpolatory quadrature, and that is that the definite integral of f from a to b is approximated by this quadrature rule. So here's the approximation, and then we have the error, which is just the integral of the interpolation error. Okay, and I hope I have enough room for this. The weights, when it's interpolatory, are always the integrals of the Lagrange polynomials for whatever nodes that you have. Okay. Okay. Wait, something is off here. Yes, I goofed. This should be just n. And n factorial. Whatever you have here should always be the number of interpolation points you have, which is n in this case, because we have n nodes. Okay, so in words, what's happening here is approximated by the exact integral of p n minus 1. Okay. That's polynomial degree n minus 1. We have n interpolation points. That interpolates f of x at the nodes x1 up to xn. Okay. Now another thing I want to bring back is the degree of interpolatory quadrature rule is at least n minus 1, because if your polynomial, if your function, your integrand f is a polynomial of degree n minus 1 or less, then the error will be 0, because it involves the nth derivative, which would be 0 in this case. Can we do better? Now, in some cases, we've seen where the degree can be n. So, for example, all right, so I'll make a note of that here. So, for example, midpoint rule and also Simpson's rule is an example of an n-node rule that has a degree of accuracy n. But can we do even better than that? Is one thing we want to take a look at today. And something else we need to examine using this kind of a quadrature, interpolatory quadrature, may not perform well if n is large due to weights, wi, these possibly being negative. For example, Newton-Cotes rules, which are perfectly fine for small values of n, but for large values of n, the weights are bound to have to be negative, some of them anyway. So the weights will still add up to b minus a, but it could be a combination of positive and negative values. So is it possible to come up with a quadrature rule that, while still interpolatory, is guaranteed to have positive weights. And Gauss Quadrature is a way to address both of these issues, trying to get the maximum degree and also ensure positive weights. Okay. All right. So, all right. Okay. So what exactly is Gauss Quadrature? All right. Something that Gauss, his name is attached to, and I believe he actually did come up with it, invented in this case. It's not true of everything after him. Although I do have to mention that my early in my time here, I think it was the second master's student that I ever had. So we're talking 2011, 2012. Had a thesis project that related to Gauss Quadrature, and he kept mispronouncing Gauss. Like the whole time he was working on his thesis with me, so we're talking about a year. He kept saying Gauche or something like that, and I keep correcting him and so forth. And toward the end, he just got real extra flustered, and finally said, something along the lines of, "My coon ass can't pronounce these words." So, yeah, he just hit his limit. So, like, okay, fine, gosh, it is. So,
I have a question. Just curious. You were a lot of stuff after Gauss.
yeah.
That really doesn't have much to do with them. Do you think people do that because they want to bring attention to whatever they just came up with? Because I would kind of want my name on it. If I came up with something. I'm really just curious.
Yeah. Well, okay. It's kind of funny how these things work, because so here's an example where I personally know the people involved. So very from numerical linear algebra, and it was long known as Lanczos bidiagonalization, and so that's reference to Cornelius Lanczos, who developed a lot of methods. He has a whole book on linear differential operators, made important contributions to numerical linear algebra. He lived until like the 70s or so. He did not develop Lanczos bidiagonalization. It was actually developed by my advisor, Gene Golub, and a collaborator of his, Bill Kahan. And now the reason it was called Lanczos bidiagonalization is it is a version of an algorithm that actually is due to Lanczos. So like Lanczos iteration, it's just applied to a matrix, and it's done in such a way as to make it more efficient and robust. So in their point of view, it made sense to call it that. And actually, it's something that I might bring up in 610 next semester. And the way Gene, my advisor, felt about it was he did not want this method named after him. And I'm trying to think, like, because the algorithm that he was best known for, his career, was an algorithm for computing the singular value decomposition, which it really was a huge deal. And I think informally that would be referred to as a Golub SVD algorithm, but not like in any official sense. So it would just be cited for it. But yeah, he did not want it named after him, and so he passed away in 2007. So then in 2010, I was at Stanford and giving a talk, and I mentioned Lanczos by diagonalization, and so one of his colleagues, who was actually his former student, like very long ago, Michael Saunders, who knows, you might have a chance to meet at a SciEm meeting someday. He told me that he was working to have that change, that it should now be called Golub Kahan by diagonalization to honor the creator. So something that Gene never would have stood for when he was alive, but now that he was no longer around to object, it was happening. And actually it did stick pretty quickly, that this change. So that it is, and I'm aware of other examples where a method name is, or something like this is changed to honor the inventor, like maybe after they passed away or something. I mean, anybody would object if, because some of you have read about my work of KSS or Krylov subspace spectral methods, and why did I call it that? Well, because the term does not. I may have developed them for my dissertation, but the term KSS or Krylov subspace spectral method does not appear anywhere in my dissertation. My dissertation talks about Krylov subspace methods for blah blah blah, and I realized later that that's kind of confusing, because when you say Krylov subspace methods, as you'll learn about in 610, people will hear that and be thinking of something else entirely. I thought, well, I need to give these some kind of name that is more descriptive than that. And I'm like, well, they are spectral methods too, and they induce ideas from Krylov subspaces, so Krylov subspace spectral methods. And after doing a quick search to make sure that no one else had used the term to refer to something else, that's the name. And I didn't even think about KSS. Someone else started using the acronym, and like, okay, fine. I personally would feel weird saying this is the Lambert's method, and if someone else wanted to attach my name to it, and that while I'm alive or dead, I don't think I'd object, really, because at least it meant they were getting attention. I feel funny doing that myself, because it seems it feels presumptuous. So that's just my feeling. But yeah, so a lot of time, I guess what we can see from the examples I've given, also examples such as Gauss elimination, which is not developed by Gauss, but he may have worked on things that are related to it. That maybe when people's names are attached to something, it might be to with descriptive purposes in mind, like maybe it's with the intent of having it associated with something else that is also well known, to help people understand what it's coming from, what it's for, or that kind of thing. So who knows? But we've also seen that things can change when there's a good reason for it. So yeah, good question.
Thanks.
Alrighty. Now, okay. All right. Now, so first I'm going to define what it is. The Gauss Quadrature rule is an interpolatory rule in which the nodes x1 and xn are the roots of a polynomial of degree n that is orthogonal of lesser degree. And this statement right here is why I had you all spend so much time on orthogonal polynomials, which normally I don't cover in a first course of numerical analysis, but it sets this up. And honestly, in other classes like Math 460, 560, where I do cover Gauss Quadrature, without covering Chapter 8, I do bring up notion of orthogonal polynomials, but I feel like it kind of limits how much I can go into the topic because I haven't covered that stuff from Chapter 8. But at least now you all have seen it. Okay. So as an example, okay. Suppose we are trying to evaluate the integral of some function f of x, and specifically on the interval -1 to 1. Okay, then the Gauss Quadrature rule for this integral that has n nodes the roots would be, the nodes would be the roots of ln of x, the nth degree Legendre polynomial. All right. So Legendre polynomials are orthogonal on the interval -1 to 1. So however many nodes you want in your Gauss Quadrature rule, you get that Legendre polynomial degree n using like the recurrence relation, the three-term recurrence relation for Legendre polynomials. Then you get its roots, and those are the nodes for your Gauss Quadrature rule. And then the weights are obtained in the same way as before. The so these are the Lagrange polynomials for those nodes. So these nodes that are these points, these x values that are nodes of the Gauss Quadrature rule, but they're also roots of a Legendre polynomial. We're going to give it a name. It's called the Gauss-Legendre points. All right. Now, all right, so how to get that? Use, as I mentioned, the free term recurrence relation. Okay. Repeatedly. Now, what if suppose we're not integrating on -1 to 1? what would you do in that case? Then you can just scale and shift the nodes and weights. So, for example, if I want to integrate on the interval 0 to 1, then what I could do is I could take the weights and cut them in half, because the interval is 0 to 1 is half the size. And then, so that would be enough for the weights. For the nodes, what I would do is I would add 1 to them. So instead of -1 to 1, they go from 0 to 2, and then divide them in half. So then they would fit within the interval 0 to 1. Now, here's a problem. Now, we're talking about a polynomial of any degree n. Now, if we're talking about a quadratic or maybe a certain number of special cases, that might not be a big deal. But if we want to deal with cases of high degree, because high degree quadrature is a problem using other nodes, what about the problem getting a roots? Well, yes, polynomial roots are difficult to get. So this is could be seen as a drawback of Gauss quadrature, that it's certainly not as convenient to get the nodes as for something else like Newton-Cotes, where there's a very simple formula for them due to them being equally spaced. Now, one thing that helps is for certain values of n, like reasonable value, like fairly small values, that there are tables out there that list the nodes and weights to quite a few decimal places, like 15, 60 decimal places, which is all the precision you could expect anyway. So if you were to Google, Gauss quadrature, like on a Wikipedia page, you would find a table that has all the nodes and weights, either decimal places or as formulas involving like radicals. So then you can go ahead and use that. That's pretty efficient, because the work of getting the nodes and weights has already been done. You're just copying the numbers and using them in your code. Now, that doesn't fit everything. It's only up to a certain degree. I don't really know what's out there, but someone's probably gone to quite a bit of trouble to make these available. So that's one thing that can be done. Now, you can use certain iterative methods. There actually is a MATLAB code out there that gives you Gauss quadrature nodes and weights for any value of n. And it's actually a fairly efficient iteration that uses the recurrence relation for Legendre polynomials. Okay. Or eigenvalue finding methods. And if time permits, actually, I might not be able to do it today, but maybe on Wednesday I can talk about both of these. Okay. So it's not ideal, but at least there are things that can be done to get these nodes and for also the weights. Okay. Now, the things we want help with when it comes to interpolatory quadrature. Degree of accuracy, we'd like a higher degree. And then after that, I'll talk about the issue of avoiding negative weights. So let's suppose your integrand f of x since degree of accuracy is all about polynomial integrands, I'll let fx be a polynomial of degree m. And at this point, m is unspecified. It's just some variable. But we'll get an idea as to how large it can be in just a little bit. Then let's see what happens when we try to carry out Gauss Quadrature to integrate f. All right. So I'm going to break f down into Pn minus 1 of x. So this interpolates f at the nodes, like in interpolatory quadrature in general. So Pn minus 1 of x refers to this Pn minus 1 of x. It's just that the nodes in this case are the Gauss Quadrature nodes. Okay. So this right here is the approximation, because the quadrature rule is about evaluating this integral exactly. Okay. And I just need to put a little note here. Dang it. Okay. All right, so just keep this in mind that this polynomial agrees with f at these points. Okay. Approximation, this is the error. Okay. So we want to see under what circumstances can we make this error equal to 0. That's the important thing. Now, since this right here that's our quadrature approximation, where the weights, remember, the weights come from integrating Lagrange polynomials. And this polynomial is equal to these f values times Lagrange polynomials. Okay. Okay. I'm gonna need to move this onto a new page. Okay. Actually, for clarity, I'm going to not jump to this step so quickly. Because they're going to have several steps anyway. Might as well get the most out of it. Pn minus 1 written in Lagrange form is f at the nodes Lagrange polynomial for those nodes. Okay, so that's the approximation part. For the error, what can we deduce here? Remember, these two polynomials are equal at these points. What does that mean? That means that this whole thing, which this is equal to 0 at these points. What does that mean? I can partially factorize it. Okay. Okay, so I need to explain this notation here. So what I have pi n is equal to x minus x1 and so on. What on earth happened here? Oh, I see. Okay. So it's equal to product of all of these. Why? These x1 up to xn are roots of this polynomial. Remember, polynomial minus polynomial. This whole thing is a polynomial. It has roots at these points because these two polynomials agree at those points. Okay. Now, so in other words, I'm able to factor out these linear factors and then out of this whole error. And then I have this is something left over. I don't really know anything about it except for one thing. F. Okay. I'm going to assume that my degree m is at least n. No, not less frequent. At least n minus 1. Because regardless of how I choose the nodes, if it's a polynomial degree n minus 1 or less, I know this is going to be exact because that's interpolatory quadrature. I'm interested in larger degrees. In fact, let's go a step further. I'm going to make it strictly greater than, because that's when it gets interesting. It's not interesting when m is n minus 1 or less, because again, I know it's exact. Okay, so what I know about this polynomial has degree m minus n, because this whole thing is of degree m. I factored n roots out of it. M minus n is what's left. So this is some polynomial of degree m minus n. I don't know what it is. Questions so far? Okay. Now, all right, so for the approximation side, I can pull out the sum and the f of xi from the integral. And then I still have the integral of the Lagrange polynomial. Okay. Now, the error part, I can think of that as an inner product of this polynomial pi n with whatever this polynomial q m minus n is. And then here we have the integrals of Lagrange polynomials. Well, those are weights because it's interpolatory quadrature. And then this inner product is my error. Okay. Now, what does this tell us? Because these nodes are the roots of a polynomial orthogonal to all polynomials of lesser degree. But these are the roots of pi n, because pi n is defined that way. Pi n is orthogonal to all polynomials lesser degree. So in other words, this inner product which is the error, is 0 if this remainder part is of degree less than, strictly less than n. So in other words, m minus n must be less than n. Or m is less than 2n. Or since we're dealing with integers, m is less than or equal to 2n minus 1. So if f is a polynomial of degree 2n minus 1 or less, the Gauss Quadrature rule is exact. So remember, Interpolating Quadrature rule has degree of accuracy at least n minus 1. But now we know, and we've seen n in some examples, but now we can do a whole lot better. This is the best that we can count on. Why? Because to have degree of accuracy 2n minus 1, that means the quadrature rule has to be exact for polynomials of degree 0, 1, 2, 3, etc., up to 2n minus 1. That's 2n constraints. What are unknowns? The n nodes and the n weights. So that's 2n variables that determine a quadrature rule. So degree 2n minus 1 is actually the highest degree that you could possibly hope for. And now we see that we can get it. All right, so that's huge advantage number 1 of Gauss Quadrature rules. They maximize degree of accuracy. So questions here? All right. Now, what about huge advantage number 2? Because having high degree of accuracy may not really be all that helpful if we can't ensure that the weights will be positive. All right. Now, now we know that the weights are equal to the integrals of Lagrange polynomials. But here's something rather freaky that goes on just in this case. I'm going to look at the integral, not of the Lagrange polynomials, but the Lagrange polynomials squared. So let's suppose I go to approximate this integral using a Gauss Quadrature rule. So then I go ahead and apply the quadrature rule with the nodes and weights. So this is squared. And then I have the weights. Okay. And generally, there would be some error here. Now, what is the degree of this integrand?
N minus.
Oh, hold on, I just realized I have a typo here. I need to fix this. I have I in here already, so my sum needs to be over a different variable. I'll use j. Okay. I'm sorry. So what were we saying? What's the degree of this of a whole integrand?
Well, I said N minus 1, but I don't know. Maybe that's not right.
Sorry, the audio got garbled.
It's okay. I said N minus 1, but maybe that's not right. I was just going.
The degree of a Lagrange polynomial by itself is n minus 1.
Yeah. But it's squared.
And what does that do to the degree?
Doubles. Nope.
Yes.
Yeah.
Okay. So now the degree of this integrand is 2n minus 2. But this is a Gauss Quadrature rule. It's exact. Polynomials up to this degree, which is 1 greater. Therefore, there is no error. This is exact. Now that we know the integral of this Lagrange polynomial squared is equal to this sum, can anyone tell me, based on properties of Lagrange polynomials, what does this whole sum condense to? Remember, these are Lagrange polynomials set up for these points. So what does that tell us? What is this equal to? Depending on the values of I and j.
Is it 0 there? I always mix it up if they're equal or not equal. I have to look back at it, and then 1 otherwise.
Okay, yes. Let's keep straight which case is which.
Yeah, I always have to go back and refer to it. I think when they're equal, it's 0, right?
No.
No. Okay, sorry. 1.
Yeah, because they'll be not equal most of the time, and they need enough roots.
Yeah.
Okay. Now, with that in mind, this whole sum simplifies incredibly. What is left after taking that into account? I mean, if it's 0 for I not equal to j, that's a lot of things going away. But what's left?
So the weight for when I equals j.
I is all that's left. Now, here's where things get a little weird, because we have a formula for wi already that was used up here. So I'll just repeat it down here. It's an interpolatory quadrature still, so it's equal to the integral of Lagrange polynomial. But it's also equal to the integral of Lagrange polynomial squared. Definitely not something that happens in general, but it happens when these are the nodes. And this is one way to show it. Another way to show it is just use orthogonality, kind of like what I did up here. Just because these polynomials agree at all the xi's, because this is equal to 0 or 1 at those points. You square it, it's still equal to 0 or 1 at these points. Okay. So now we have two formulas for weights. Now, the reason why this formula is of interest, though, is what are we doing here? We are integrating a function that is guaranteed to be non-negative. And because the Lagrange polynomial is certainly non-zero, this is huge. It's guaranteed to be positive. That is, honestly, I feel like that's the real magic of Gauss Quadrature. It's not just the degree of accuracy. That's what most people tout about advantage of these rules. But the fact that no matter how large n is, the weights are positive, something that does not happen if Newton codes, not even close. Like I said, after n greater or equal to 11, there's no hope anymore. But here, for all n, weights are guaranteed to be positive. And that's not something that you could deduce from this, because look, this Lagrange polynomial is both positive and negative. But from this, you can see, oh, yeah, it's got to be positive. So we're accurate and robust. Things that we definitely want to have from our numerical algorithms. Efficiency-wise, well, once you have the nodes, then yes, they're efficient. But getting the nodes, if you don't have them for this particular Gauss Quadrature rule, can be a pain. Like I said, the information's out there about having nodes to many decimal places, so that certainly helps. Okay. Now, so the last thing I want to talk about today, I think it's the only thing I'll have time for, and this relates directly to the homework. So I have put out the homework problems for this section. There are only 3 of them. Okay. So now I've discussed the error for interpolatory quadrature in general. So in the general case with an interpolatory, the exact integral is equal to the quadrature approximation plus the integral of the error, the interpolation error. So this interpolates f at the nodes. Okay. So the error formula so to use the interpolation error formula, theorem 7.4.1. It describes the error in that kind of interpolation. But while you could technically use that for Gauss Quadrature, it actually does not really give you the whole picture as to the error. What we have in Gauss Quadrature is this. Okay, so first part of it I will keep. So here, instead, we have the Hermite interpolating polynomial. Okay. So then we use the interpolation error from theorem 7.5.1. So that's what gets filled in here. Now, here's the really strange part. Because the approximation is always the integral of the interpolating polynomial, and then the error is the integral of the interpolation error. So what we would normally have is the integral of the interpolating or Hermite interpolating polynomial. Well, how do we write the Hermite polynomial? That would be a sum of fxi times h of these h's plus f prime of xi times these k's. Okay, and then all of this is integrated. Okay. So we're supposed to believe that the integral of all of this somehow condenses to the integral of this summation here, where the weights are equal to the integrals of the Lagrange polynomials or Lagrange polynomials squared. But this seems a little odd because, okay, we have a sum and we have f values. So they might think, okay, maybe the integrals of these polynomials that were defined in section 7.5 will give you weights. But what about this? Because these f prime values, how do we know that these disappear? That doesn't seem to make sense. So that's a homework problem to see how it's actually perfectly fine to use the Hermite interpolant, even though the Hermite interpolant depends on the values of f prime at the nodes, and yet the approximation does not use values of f prime at the nodes, or doesn't use f prime at all, because I mean we don't want to do that. We don't want to use derivative values when we're trying to integrate just plain old f. So one of actually two of the homework problems are to look into this. The other homework problem has to do with what is called direct construction, because, as I mentioned, the nodes and weights. Okay. And what's direct construction? That means you're finding the nodes and weights to maximize the degree. Like, you know what kind of degree you're supposed to get. It's 2n minus 1. So you require this quadrature rule to match the exact integrals for polynomials, x to the 0, x to the 1, and so forth, up to x to the 2n minus 1. And you have a system of equations to solve for the nodes and weights. The problem is, okay, it's a system of n plus 1, or sorry, a system of n equations and n unknowns. The problem is this system of equations is not linear. We've seen linear equations play a role, for instance, like the normal equations for finding best two normal approximation, polynomial. That's something we talked about very recently. Also, solving a system of linear equations for polynomial interpolation, like if you're using a van der Waals matrix. Okay, linear systems, that's fine. It can still be quite a bit of work, but readily doable. There's a standard, relatively simple algorithm for doing that. But when you're trying to solve for the n nodes and n weights that will get 2n integrals exactly correct, because the nodes are raised to powers of x, that leads to a system of nonlinear equations. Okay. Actually, I have just enough time to give a quick example. Okay. So if n equals 2, so 2 nodes, 2 weights. Okay. So what we can say is, so x1 to the 0 power, weight 1 plus x2 to the 0 power, weight 2 is equal to the integral from a to b of 1. Now, this just becomes w1 plus w2, which ought to be equal to this, which is b minus a. Okay. Then the next equation, raising the nodes to the first power. And that'd be the integral of x. And then we square. And then finally cubed. Because a 2-node rule should have degree of x be 2n minus 1. Okay. So then I have w1 plus x2 cubed, w2, and that should be the integral of x cubed on AB. So here we have 4 equations that must be satisfied by the 4 unknowns, 2 nodes, 2 weights. But because they're multiplied together and the nodes are raised to powers, that's a nonlinear system of equations. So kind of a pain. But the n equals 2 case is doable, so I've assigned that for homework. So you can have fun trying to solve for those nodes. Now, it's a 2-node Gauss Quadrature rule, so you actually can look up the answers just to check your algebra. But I thought that'd make it a little more humane. Okay. I just certainly all the time I have to cover stuff today, but I'll have some interesting Gauss Quadrature related problems to examine for tomorrow or Wednesday. Do you have any questions about any of this? Weird how it keeps flashing. I don't know what that is. Okay. All right. Well, sure, we're all brain fried anyway. I know I am. Okay. So only one regular class left to go. Okay. So good luck with all the homework I've dumped on you. At least I will dump no more. And we'll see how things go down this home stretch. All right. I'll stop recording here.